Hi, our topic for today is about differentiation of vector valid function. So in this lesson, you should be able to differentiate a vector valid function. Okay, what is the derivative of a vector valid function? The derivative of a vector valid function r is given by this equation. This is read as r prime of t equals the limits of r of t plus delta t minus r of t over delta t as delta t approaches 0 for all values of t for which the limit exists. If r prime of t exists, then r is said to be differentiable at t. If r prime of t exists for all t in an open interval I, then r is differentiable on the open interval I. Differentiability of vector valid function can be extended to closed intervals by considering one-sided limits. Differentiation of vector valid functions can be done on a component-by-component basis. So to see why this is true, consider the function r of t, which is equal to f of ti plus g of tj. So by applying the definition of the derivative produces the following. R prime of t is equal to the limits of r of t plus delta t minus r of t over delta t as delta t approaches 0. But recall that r of t plus delta t can be obtained by replacing all the t variable of r of t by t plus delta t. So this can be written as f of t plus delta t times I plus g of t plus delta t times j. Okay, minus r of t, where r of t is f of ti minus g of tj, all over delta t as delta t approaches 0. And then combining those terms with I component, so we have f of t plus delta t minus f of t all over delta t times I. Plus, we combine those terms with the j component, so you have g times t plus delta t minus g of t all over delta t times j. But recall that the limits of f of t plus delta t minus f of t over delta t as delta t approaches 0 times I is the same as the derivative of f of t, which is f prime of t. Plus, recall also that the limits of g of t plus delta t minus g of t all over delta t as delta t approaches 0 is the derivative of g of t, which is g prime of t times j. So therefore, the derivative of r of t is equal to the derivative of the ith component plus the derivative of the jth component. Okay, so let us now summarize the differentiation of vector valid function using this theorem 12.1. That number 1, if r of t is f of ti plus g of tj, where f and g are differentiable functions of t, then r prime of t is the derivative of f of t times I plus the derivative of g of t times j. Or this can be read as r prime of t equals f prime of t I plus g prime of tj in two-dimensional space. Okay, number 2, if r of t is a vector valid function in three-dimensional space, which is defined as f of ti plus g of tj plus h of tk, where f, g, and h are differentiable functions of t, then the derivative of r of t denoted by r prime of t is equal to the derivative of its component. So we have f prime of ti plus g prime of tj plus h prime of tk. Okay, note that the derivative of the vector valid function r is itself a vector valid function. So as you can see in this figure, you can see that r prime of t here is a vector tangent to the curve given by r of t and pointing in the direction of increasing t values. Okay, so as an example, suppose you're given a vector valued function r of t, which is equal to ti plus t squared plus 2 times j. So in this case, we need to find the first derivative of this vector valued function. And then we need to sketch the plane curve represented by r of t and the graphs of r of 1 and r prime of t. Okay, so the first thing that you have to do is differentiate this vector valued function on component by component basis. So the derivative of r of t is r prime of t equals the derivative of the first component, which is 1 times I. So you have I plus the derivative of t squared plus 2, which is 2t times j. And from the given vector valued function, we can identify the x and the y component. And so the corresponding parametric equation is of this form: x equals t for the first component and y equals t squared plus 2 for the second component. And then after that, we can now obtain the rectangular equation of this parametric equation by substitution. You substitute the first equation to the second equation to get y is equal to t squared, where t is x, so this should be x squared plus 2. Okay, so this is the corresponding rectangular equation. So in standard form, you can write this as y minus 2 equals x squared. So this is a parabola, vertex at 0, 2. And this is opens upward. And then when t is equal to 1, the specific vector can be obtained by substituting the value of t to the given vector valued function. So you have r of 1 equals ti, where t is 1, so you have I, plus, if I is 1, 1 squared is 1 plus 2, so you have 3 times j. So when t is equal to 1, r of 1 is 1 plus 3j. And for the first derivative of r of t, where t is equal to 1, is equal to I plus 2t, but because your t is 1, so you have 2 times 1 is 2 times j, so you have 2j. So the first derivative of r of t at t is equal to 1 is 1 plus 2j. Okay, from the previous slide, the vertex is at 0, 2. So to locate this point, you scale, since x is 0 and the y coordinate is 2, so you scale 2 units along y axis, but 0 for the x-axis. So this point is the vertex with coordinate 0, 2. Then from the equation y equals x squared plus 2, if x is equal to 1 by substitution, the y coordinate is 1 squared plus 2 is 3. And if x is negative 1, negative 1 squared is also 1 plus 2. So y is also 3. So the points on the parabola are 1, 3, and negative 1, 3. So this is the point 1, 3, and negative 1, 3 is 1 unit to the left along the negative x-axis, and then 3 units upward. So this point therefore is negative 1, 3. Then connect the vertex with these 2 points to draw the parabola. And then to plot the vector r of 1, which is I plus 3j. So from the origin, you scale 1 unit for the along the x-axis and 3 units upward. So this point is the terminal point of this vector r of 1. So connect the origin and the terminal point. So we now have this vector I plus 3j. And then to sketch the first derivative of r prime of 1, we use the terminal point of r of 1 as the origin. And then from here, you scale 1 unit along the direction of the x-axis. So you have 1 unit and then 2 units upward. So 1 and then 2. Okay, so this point is the point with coordinates 1, 2. So connect this terminal point of vector r of 1 and the terminal point of this vector r prime of 1. So we now have this vector r prime of 1. So as you can see, this vector r prime of 1 is tangent to this curve given by r of t, and this is pointing in the direction of increasing t values.